Welcome back to AI Quantum Secure. In the world of cybersecurity, we're often told that quantum technology represents the ultimate finish line, a destination where encryption becomes mathematically unbreakable. We rely on the absolute laws of physics to guarantee that our data is safe from even the most powerful adversaries. But here is the forensic truth. While quantum theory provides a mathematical perfect lock, the physical hardware we use to build that lock acts as a keyhole with inherent, unintended flaws. We are no longer just fighting algorithms, we're fighting the limitations of silicon, light, and electricity. Today, we're moving beyond the blackboard to explore the real-world vulnerabilities that live inside the machines. This is quantum security. Closing the hardware keyhole. On your screen is our comprehensive matrix of the current quantum threat landscape. Our mission today is to dissect the hardware gap, the space between a perfect mathematical proof and a messy physical component. On the left, we identify the theoretical vulnerabilities that compromise the hardware keyhole. These aren't failures of physics, they're exploitations of behavior. Detector blinding, where high-intensity pulses force sensitive quantum sensors into predictable classical behavior. Photon number splitting, known as the quantum tap, where attackers siphon off redundant photons to leak keys without ever disturbing the original signal. Time shift and Trojan horse attacks, which exploit picosecond timing gaps and optical echoes to read internal modulator settings before the data ever leaves the device. However, the focus of AI Quantum Secure is not just identifying flaws, but engineering resilience. On the right, we move into the matrix of engineering defenses. This is how we fight back. We integrate power monitoring to block blinding attempts, decoy states to expose photon siphoning, and gate shaping to eliminate the timing windows used in precision attacks. As we look at the comparison table at the bottom, notice the pattern. For every hardware weakness, there is a specific engineering defense. This briefing will take you through each of these case files to show you exactly how the Unbreakable is broken, and, more importantly, how we can use advanced engineering defense to close the hardware keyhole for good. Let's dive in.
The Physics Implementation Gap. Welcome to AI Quantum Secure. You are looking at the fundamental paradox of modern cryptography. On the left side of your screen, we see the theoretical stability of a quantum key distribution link. In this idealized realm, the laws of physics are absolute. When John sends a stream of qubits to Jennifer, the no-cloning theorem acts as a universal sentinel. The math tells us that any attempt by an adversary to intercept, measure, or copy a quantum state must, by definition, introduce detectable noise. This is the unbreakable promise. The sine wave you see is clean, predictable, and mathematically perfect. In the classroom, this is where the conversation ends. We assume that because the physics is secure, the system is secure. But at AI Quantum Secure, we know that theory doesn't live in a vacuum. It lives in hardware. The shift to reality. As your eyes move to the right of the center line, notice the transition. The smooth blue frequency of theoretical stability shatters into the jagged red chaos of physical implementation. This is where the laboratory meets the silicon. When John and Jennifer set up a real-world QKD link, they aren't using mathematical symbols. They're using lasers, fiber optics, and avalanche photodiodes. These devices are built by humans, and humans build imperfections into everything they touch. Detectors have dark counts, lasers have Poissonian fluctuations, modulators have mechanical drift. To an attacker, these aren't just technical annoyances, they are the blueprints for a total system compromise. Defining the keyhole.
The red region of the slide highlights vulnerability exploits and hardware compromise detected. This visualizes the core philosophy of this channel. Physics is the lock, but the hardware is the keyhole. An adversary doesn't need to break the lock of quantum mechanics. They don't need to violate the Heisenberg uncertainty principle or defeat entanglement. They simply need to manipulate the keyhole, the hardware interface, to force the system to behave in a classical way. As we see in the data exfiltration risk markers, a hardware exploit allows the key to leak out silently. By attacking the physical layer, an eavesdropper can extract John's secret keys without Jennifer ever seeing the spike in the quantum bit error rate that she's been trained to watch for. This briefing is titled Closing the Gap Between Theoretical Security and Physical Implementation because awareness is the first step in defensive engineering. Throughout this series, we are going to dissect the most devastating side-channel attacks ever demonstrated in a lab. We will look at how John's imperfect laser source allows for quantum tapping through photon number splitting. We will explore how Jennifer's detectors can be blinded by classical light, forcing them to obey the attacker instead of the quantum signal. We will even see how picosecond shifts in timing can lead to a full key compromise. In the world of AI quantum secure, we don't trust the math until we've audited the hardware. Join us as we look under the hood of the quantum revolution to see what's really happening when the photons hit the silicon. Let's break the illusion of perfection and start building real-world security. The core conflict: math versus manufacturing. As we open our cyber forensic briefing, we have to confront a hard truth. The physics is perfect, but the engineering is messy. In the mathematical models that John and Jennifer rely on, every laser pulse is a single, isolated photon, and every detector is a perfect, tireless observer. But the manufacturing floor is not a whiteboard. Real-world components introduce side channels, unintentional leakages of information that have nothing to do with quantum mechanics and everything to do with hardware limitations. Our mission today is to dissect the hardware gap, that dangerous space between the mathematical ideal and the physical component. We have organized this briefing into 4 specific case files, each representing a unique way an adversary like Eve can bypass Jennifer and John's security without ever breaking a law of physics. Case File 01, the Coercion. Our first investigation, Case File 01, covers detector blinding. We call this coercion because Eve isn't sneaking past the detector, she is taking it over. By hitting Jennifer's hardware with a high-power classical pulse, Eve forces the system out of its quantum state and into a predictable classical mode. In this state, the detector is no longer an independent judge of quantum truth. It is a puppet that only clicks when Eve pulls the strings. This exploit is devastating because it maintains the illusion of security while the hardware is fully compromised. Case Files 02 and 03, Theft and Timing. Moving to Case File 02, we look at photon number splitting, or theft. This exploit targets John's end of the link. Because John's laser isn't perfect, it occasionally leaks extra photons. Eve doesn't need to copy a qubit. She simply steals the extra one John accidentally provided. Because the original photon still reaches Jennifer, the theft remains invisible. Next, Case File 03 investigates time shift attacks. Here, the vulnerability isn't in the light, but in the timing gaps between Jennifer's detectors. By manipulating the exact picosecond a photon arrives, Eve can exploit the fact that no 2 detectors are perfectly identical. She uses the hardware's own timing mismatches to steer the measurement outcome, ensuring she knows the key while Jennifer and John remain in the dark. Case File 04 and the defensive objective. Finally, Case File 04 covers the Trojan horse, an active probing attack. In this scenario, Eve doesn't just wait for John to send a signal, she sends her own probe beam into his device to read his internal modulator settings. It's the quantum equivalent of a bugged room, where John's own hardware echoes his secrets back to the attacker. But we aren't here just to list failures. The ultimate objective of this briefing is to move from vulnerability analysis to defensive engineering strategies. For every exploit Eve has developed, there is a countermeasure, a way to harden the hardware and bridge the gap. By the end of this session, you will understand not just how the Unbreakable is broken, but how we can use AI and advanced engineering to fix it. Let's dive into the evidence.
In this third stage of our briefing, we move from the abstract hardware gap to the specific paradox that makes Jennifer and John's link vulnerable, the hardware physics paradox. This is the root cause of every exploit we will discuss. On the left, we see the lock, quantum theory. This is the world of the classroom and the research paper. It is a realm that assumes ideal qubits and mathematically proven security with zero noise. In this theoretical space, as long as John and Jennifer follow the protocols of physics, their communication is essentially a fortress with an unbreakable lock. However, on the right, we see the reality Jennifer and John must actually build, the Keyhole, hardware implementation. Real-world security does not rely on equations. It relies on lasers, diodes, and modulators. Unlike the perfect wave of theory, these physical components are subject to variance, background noise, and imperfect efficiency. This is the most critical lesson of this briefing. Physics is the lock, but hardware is the keyhole. An attacker like Eve does not waste her time trying to pick the quantum lock. She knows the math is sound. Instead, she looks for the imperfections in the keyhole, the physical hardware John and Jennifer used to build that lock. This implementation layer is exactly where Eve hides. By exploiting the subtle differences between how a component should work in theory and how it actually behaves in silicon, she can bypass the quantum protections entirely. As we move forward, keep this paradox in mind. We aren't looking for a flaw in the universe, we are looking for a flaw in the machine.
In this technical deep dive, we examine Case File 01, Detector Blinding, a devastating exploit where Eve coerces Jennifer's quantum sensors into behaving like classical devices. This attack targets the single-photon avalanche diode, SPAD, the heart of Jennifer's receiver. To understand this exploit, look at the SPAD response graph. Normal operation, Geiger mode. Under standard conditions, the detector operates in Geiger mode, where it is hypersensitive. A single incoming photon triggers a sharp digital voltage spike, allowing the system to register quantum information with high precision. The blinding pulse. Eve intervenes by shining a high-intensity blinding pulse into the fiber. This massive influx of light saturates the SPAD, overwhelming its quantum sensitivity. Once saturated, the detector is pushed out of Geiger mode and into linear mode. In this state, the hardware is blind to individual photons. It no longer produces digital clicks from John's quantum signals. Instead, it acts like a classical sensor that only responds to the high power pulses Eve chooses to send. The exploit in practice: by holding the detector in this blinded, linear state, Eve gains deterministic control. She can dictate exactly when Jennifer's hardware clicks by sending her own bright classical pulses. Because these pulses produce clean results without the noise typically associated with eavesdropping, Jennifer and John may never realize their unbreakable key has been compromised at the hardware level. The engineering defense: to close this keyhole, we implement power monitoring. This defensive strategy uses a watchdog circuit to continuously track input intensity. If the light levels exceed the strict single-photon threshold required for Geiger mode, the system identifies the anomaly as a blinding attempt and immediately aborts the protocol. By auditing the power hitting the silicon, we ensure that Jennifer's hardware remains in the quantum regime where it belongs.
In this technical deep dive, we examine case file 02, photon number splitting, or the quantum tap. This exploit targets a critical hardware imperfection in John's transmitter, the fact that real-world lasers often follow Poisson's statistics. While the theory of KKD assumes John sends a perfect single-photon pulse every time, the physical reality is that his laser occasionally emits a multi-photon pulse. The exploit: zero disturbance, 100% leakage. Eve uses a beam splitter to intercept the signal between John and Jennifer. From a multi-photon pulse, she peels off a stolen copy and diverts it into her own quantum memory. The undisturbed signal continues to Jennifer. Because Jennifer receives the photons she expects with the correct timing and polarization, she detects no error. Eve simply waits for John and Jennifer to announce their basis over the classical channel, then measures her stored photon to extract the key with absolute certainty. The defense? Decoy states. To close this keyhole, we implement decoy states. John intentionally mixes in dummy pulses with varying intensities. If Eve attempts to siphon photons, she inevitably alters the statistical ratio of these decoy states. By monitoring these statistics in real time, Jennifer can immediately detect the presence of the tap and abort the key generation before any data is compromised. In this final deep dive of our cyber forensic briefing, we examine case file 03, the time shift attack, an exploit that targets the subtle temporal imperfections in Jennifer's hardware. While quantum theory assumes that detectors are identical and perfectly synchronized, physical manufacturing tells a different story. The exploit: hiding in the efficiency mismatch. The core of this vulnerability lies in the detector efficiency mismatch. In a real-world system, Jennifer's two detectors, labeled here as Detector 0 and Detector 1, do not wake up at the exact same picosecond. As shown in the graph, Detector 0 peaks at 100 picoseconds, while Detector 1 is slightly offset, peaking at 120 picoseconds. Eve exploits this gap by manipulating the arrival time of John's photons. By precisely shifting a photon's arrival to land within Eve's timing window, around the 100 picosecond mark, she ensures that Detector 0 is at near maximum efficiency, while Detector 1 is effectively deaf to the signal. This allowed Eve to blind one detector relative to the other simply by changing when a photon arrives, giving her the ability to steer the measurement outcomes without ever touching the quantum state itself. The engineering defense: gate shaping and efficiency matching. This defensive strategy involves two critical steps: calibration. Engineers must meticulously calibrate detectors to ensure they have identical temporal windows, neutralizing the mismatch Eve seeks to exploit. And narrowing the acceptance gate. By tightening the detection window to exclude the mismatched tails of the efficiency curves, we leave no room for Eve to hide her timing shifts. By mastering the picosecond level behavior of our hardware, we ensure that Jennifer and John's link remains secure against even the most subtle temporal manipulations. In this final case study, case file 04, the Trojan horse, we examine an active probing attack that targets the internal configuration of John's transmitter. While quantum protocols assume that the internal state of a device is a black box, the Trojan horse exploit proves that hardware can be forced to leak its own secrets through optical echoes. The exploit: reading the internal mind.
The exploit is analogous to shining a flashlight into a window to see what's happening inside a locked room. Active injection. Eve sends a bright classical probe beam into John's device, typically through the same fiber used for the legitimate signal. The interaction. This probe beam travels deep into the hardware, reflecting off the optical phase modulator. The leakage. As the beam reflects back out as an optical echo, its intensity is physically modulated by John's current internal settings. Reconstruction. By analyzing the amplitude of this return signal, Eve can reconstruct John's basis settings in real time. This allows her to know exactly how to measure the qubits before they even reach Jennifer, rendering the quantum protections useless. The defense, optical isolators. To secure the hardware keyhole against active probing, we deploy optical isolators. One-way valves. These components act as one-way valves for light, allowing John's legitimate photons to exit the device while effectively blocking any external probe beams from entering. Hardening the interface. By installing these isolators at the device interface, we ensure that the internal modulator state remains a black box that cannot be queried by an adversary. With this final defense, we move from analyzing individual vulnerabilities to a holistic strategy of defensive engineering, ensuring that the unbreakable promise of quantum physics is finally upheld by the hardware that implements it. In this final session of our briefing, we conclude with the defense matrix, a strategic overview that synthesizes our forensic findings into a roadmap for engineering resilience. Throughout this series, we have demonstrated that while the laws of physics provide a perfect lock, the hardware used by John and Jennifer acts as a keyhole that must be meticulously secured. The matrix on your screen represents the front line of defensive engineering. Detector blinding. We neutralized the threat of APD saturation, the forced transition from Geiger to linear mode, by implementing power monitoring for real-time saturation detection. PNS attack. To counter the quantum tap caused by the Poisson statistics of multi-photon pulses, we deployed decoy states, creating statistical traps that expose any attempt to siphon keys. Time shift. We addressed the efficiency mismatch and temporal offsets between detectors through gate shaping, utilizing temporal filtering to close the picosecond windows where Eve hides. Finally, we secured the device against back reflections and optical transparency by installing optical isolators, providing one-way filtering that prevents any external probing of John's internal settings. The lesson for the AI quantum secure community is that true security is found in the gap between theory and implementation. By moving from vulnerability analysis to these active defensive strategies, we ensure that the promise of quantum encryption is not just a mathematical ideal, but a physical reality. We conclude with the defense matrix, a strategic overview that synthesizes our forensic findings into a roadmap for engineering resilience. Throughout this series, we have demonstrated that while the laws of physics provide a perfect lock, the hardware used by John and Jennifer acts as a keyhole that must be meticulously secured. The matrix on your screen represents the front line of defensive engineering. Detector blinding. We neutralize the threat of APD saturation, the forced transition from Geiger to linear mode, by implementing power monitoring for real-time saturation detection. PNS attack. To counter the quantum tap caused by the Poisson statistics of multi-photon pulses, we deployed decoy states, creating statistical traps that expose any attempt to siphon keys. Time shift. We addressed the efficiency mismatch and temporal offsets between gates through gate shaping, utilizing temporal filtering to close the picosecond windows where Eve hides. Finally, we secured the device against back reflections and optical transparency by installing optical isolators, providing one-way filtering that prevents any external probing of John's internal settings. We have reached the conclusion of our cyber forensic briefing, closing the keyhole. While we cannot change the fundamental laws of physics to make manufacturing perfect, we can design advanced systems that acknowledge and mitigate these physical imperfections. As we review the hardened architecture on your screen, you can see the results of our defensive engineering strategy. The APD detector is now shielded by real-time power monitoring to prevent coercion. The laser source is protected by decoy state protocols to neutralize siphoning. The optical phase modulator is secured with one-way isolators to block probing. All of these components are overseen by a secure FPGA controller that ensures the hardware remains in a trusted state. This brings us to the future of our field, device-independent QKD. We are moving toward protocols that remain unconditionally secure, even if the underlying hardware is untrusted, flawed, or manufactured by a third party. By assuming zero knowledge of the internal hardware, we ensure that security is derived strictly from the quantum correlations themselves, finally closing the hardware keyhole for good. The mission of AI Quantum Secure is to bridge the gap between theoretical promise and physical reality. Thank you for joining us in this investigation. Stay vigilant, stay secure, and we will see you in the next briefing. Thank you for joining this deep dive. Hit the subscribe button to stay at the forefront of the quantum era. Let's keep the future secure.